Hello? 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 Afternoon. I've sent another link for the new schedule, so it's even on. I'll ask your class rep to share the link so that everyone now can log in. I think this one will make it. All right. Muted myself. My goodness. Hello? Um, Hello? Hello, Bridget. Hello? Bridget,
Yes,
are you able to get me now? Hello?
I
Hello?
can get you. We can hear you.
Okay, it's now better.
Yes, it's better now.
Okay, wonderful. Okay. So going forward, I'm going to unmute all of you because we don't want to have those disturbances. This one is talking, this one is talking. So I just want to be talking alone. So if you want to communicate something, just use the chat. Just click on the chat where you can send a message and then I'm able to respond. Okay. Let's wait a few minutes for others to join in so that we can at least cover a good number of students. Mhm. Hello, Kaunda. This is Valikunda. Are you able to get me? Bridget? Hello?
Yes.
Okay. That's at the
Yes,
number.
I can get.
Okay, the number of participants are a few. So let's wait a few minutes so that quite a number can join us. So that we can begin after that. Kindly mute yourselves and only unmute yourself when you want to ask a question. So you don't want to get those background noise. So just mute yourselves. Okay, let's begin. Those who join us later, they will find us on our way. So, like I said, for anything that you want to ask, you can post a chat or you can unmute yourself and then ask yourself the question. So today we are going to look at simple. Okay. Okay. Are you able to see the notes? Are you able to see the notes?
Yes.
Oh,
There we go.
okay. So today we'll look at a simple vapor compression refrigeration system. We had just finished the air cooling system for these aircrafts. So now we are now going to look at the common one, those which you see around the fridges, the air conditioning system in malls and other places. This is the system which is being employed in most of the places. Okay, so how better is this system than the other one which we had looked at? So we're going to look at some of the advantages this system has over the air system and some of the disadvantages. So this system, it employs a working substance, which is called a refrigerant. So this refrigerant is able to condense and evaporate, meaning it's able to change phase, okay? It's able to change phase. So air does not change phase, but this refrigerant is able to change phase. As it changes phase, it is able to repeat a lot of it or release a lot of it. So Some of its advantages is that it has got a smaller size in that for a given capacity, in that it requires little amount of a refrigerant, that is the mass. Since it's liquid and it's able to change the phase, meaning even a small amount of liquid will be able to pick a lot of heat. Okay, so hence there's no need to have a big compressor, a big evaporator. So the system can be very small. Take an example of these water coolers that we have in homes, water dispensers. They are very small. And then some are portable. You can carry them, put them on the table. And then they're employing this system because of the refrigerant having the ability to change phase and pick up a lot of heat and remove a lot of heat from the substance to be cooled. It has a less learning cost. Some of you who have been in some homes where you have got a fridge, you can't even remember the last time the fridge was taken for repairs. If you look at the fridge, the main component which is there is a compressor. And that compressor is sealed in, okay? It's in a confinement. Such kind of compressors are called HEMIC compressors. So those HEMIC compressors, meaning there's no dust which gets in, there's no things that moves around. So you find that they can last years without maintenance. So the running cost is very low for such kind of systems as compared to the air system where maintenance has to be employed after some years. It can be employed over a large range of temperatures, okay? So because of its ability to change phase, it has got provision where you can change the temperature. Just like the way you change the temperature in the fridge, there is a knob to change the temperature where you can set it at a lower temperature and at higher temperature. So it can pick up and then operate at those temperatures. The coefficient of performance is quite high, yes, because it has got high ability to achieve or to extract it compared to the amount of work that is being done by the compressor. We are employing a small compressor, 1/4 compressor, 1/8 compressor. So those compressors are very small as compared to the amount of work or the heat that is being removed. So you find that the efficiency, which is the COP, for these systems are quite high. Okay. Despite all these good things about it, it has also the disadvantage or the drawbacks. Okay. So the initial cost is high. That's why when you go to buy a fridge, the upright one, it's not that cheap. It's high because of the components and the refrigerants is expensive. So the such things makes it very expensive. And the prevention of leakage is a major problem in vapor compression system. You know, the last time we talked about the air, and one of its advantages is that the leakage in small amount of air is not that of great concern to the engineers. Reason being that the air refrigerants are being picked in bulk, but in these systems, the refrigerant is in small quantity. That implies that if there is small leakage from this small quantity, then there will be a compromise on the pressure as well as the temperatures it's going to pick. So we find that if there is a leakage in the system, then the fridge stops cooling or the system stops operating normally. So it's critical. These leakages has to be avoided. You know, people like those who sell things like Coca-Cola, Fanta in shops, you find that the deep freezer is filled up with all sorts of commodities, and then they allow the customer to pick up from those deep freezers. You know, the evaporator is just around the walls of that fridge. So if there is any impact on those walls, then there will be depressions on the pipes of the evaporator, which may lead to the leakages and eventually have the fridge failing to provide the cooling. So even when you are putting food in the cooler, in the fridge, don't press it against the walls of the fridge because you're going to damage the evaporator conduits. Okay, make sure that things are in between, they're not leaning against the wall to prevent these damages and to avoid also the leakages. Okay, let us look at some of the comparison between the gas cycle and the vapor cycle. Very soon we'll look at the vapor cycle and how we are going to employ it to solve some problems. Huh? Okay, so we see that in a gas cycle, the working fluid is gas itself and doesn't undergo any phase change. So meaning when you put up these systems, when you put up the TS diagrams for these, they'll be different. Of course, they'll be different. Let me just try to draw and show you how different this will be. So a TS diagram will be different because you're using different working fluid. This is gas and the other one is a liquid. So this is how the TS diagram will be. So we'll start by putting down the TS diagram for gas. Okay.
Excuse me, sir.
Are you able to see this?
Yes, sir, we can see. Can you give us permission to record the class?
No, I'm recording it, then I'll share it.
Okay, sir, thank you.
All right. So this is a TS diagram for the gas cycle, the one we have been just doing, where we have got this is a S. So to draw this one, how the system was moving, you start with one process in isotropic compression, and then probably if there is no reversibility, then you consider the next point. Okay. And then the speed, you consider this is compression now, and then you pick up the change in pressure. It's not easy to draw here, like what we draw on the board. So let's pick up the change in pressure, and then we have got now expansion process happening there. Okay. And then there is also this cabin pressure there. This cabin pressure. Okay, something like that. So for these points, this is how the diagram will look like for simple air cooling system. This is how it will look like, a TS diagram. But let's put up the TS diagram for the compression or the refrigerant, liquid refrigerant. Okay, it's the same TS diagram in temperature against entropy. This is how it will appear. Meaning, as you change this refrigerant, there will be change in how the TS diagram will appear. Okay, and let's employ the okay. So remember this, huh? So in compression cycle, we have got these processes for extraction of heat or in evaporator represented by a constant pressure line, and then from there we see a situation where you have to compress, and then the compression, since it's centropic, you consider that it will be just a straight line, and then we see that this region where this is vapor compression and it's superheated. So to come back to the condenser, it will take some path, okay, which I will explain very soon. All I want to show you is the difference between these two in terms of the diagram. Huh? So there you are, and then it follows the constant pressure there line. From there, since this is a photo process, there will be always isentropic process. So this is how it will appear. So you can see the differences between the two. So because of the change in the refrigerant, this is what has happened. Okay, so this is actually what has happened because of change in refrigerant. Let's move on and look at some of other things that we may compare. So in a gas cycle, heat rejection and refrigeration takes place as the gas undergoes sensible cooling and heating. So there's no change in phase. What happens is the heat, as it is being picked, there is just increase in temperature in this refrigerant, which is gas. Huh? So there's no change, meaning it can't change from gas to liquid. Air will always be air. I know sometimes you can liquefy air, but in this case, this will be just a gas. In a vapor cycle, the working fluid undergoes phase change, and the refrigeration effect is due to evaporation of refrigerant liquid. So when we say refrigeration effect, the absorption of heat. So as the liquid is passing through those pipes in a evaporator, the heat that comes from the things in the cabin of the fridge, the heat that comes from the room, okay, the space, the shopping malls, and any other place, that heat is being absorbed by the cold fluid inside those pipes, and as this liquid absorbs that liquid, that heat, it vaporizes. So by virtue of it changing that phase, meaning it's picking up the heat, so the heat is being moved and then it's changing that phase. So in changing the phase, it is able to absorb a lot of heat. Okay. So if the refrigerant is pure, okay, is a pure substance, okay, the absorption of this temperature or the heat from a space has to be done at a constant temperature. So which we call as a thermal process. Huh? So meaning you are not changing the temperature to which you are absorbing the heat. Meaning the temperature gradient between the thing which is releasing the heat and the thing absorbing is maintained, meaning it's big. Some refrigerant can have the evaporator temperature as low as -40, as low as -48. So meaning the temperature gradient between the things to lose heat and the thing to absorb it is very big. Meaning all the heat, whatever thing you put in the fridge, it will still lose the heat because the temperature gradient is big and it's not being reduced. The temperature at which you're absorbing this heat is constant. So by virtue of it taking that path or that law, it is able to absorb a lot of heat as compared to this gassy cycle. So the mass flow rate, I've explained on the mass flow rate. For the air, we need a lot of mass, okay, for it to carry the heat. But for this liquid refrigerant, it's just a small amount, which is possible for you to achieve the cooling. So vapor cycle can be divided into compression system, which you are looking at now, okay, which is mostly employed in most systems. And other vapor system, vapor cycles, which you have around, is the next topic, yeah? Vapor absorption system, vapor jet system, okay? So these are other systems which we'll look at, okay, in the next topic. Let's move on and explore more on how this system works. How better is this system than the previous system, okay? So we see that highly compressed fluid at certain temperatures tend to get colder when they're allowed to expand. So like in the expansion device. So you expand this highly compressed fluid and then it will get colder, minus, okay? So if it gets colder, then it's able to pick more heat. And then if you compress it, it will be at higher temperature. You know, the process of losing heat to the environment naturally is by allowing hot high temperature environment to lose it to the colder environment. So the temperature difference between these two bodies which are sharing the heat has to be big. So that's why we employ a compressor to increase the temperature. So when you compress, the temperature of this liquid refrigerant will go up at higher temperatures, and then it's able to release that heat to the environment without any problem. Okay, let us look at two advantages. The first one is a large amount of thermal energy is required to change liquid to vapor. Just like the way when you are cooking, when you are cooking or steaming water, you put your pot on the stove and you put water in there, you turn on the stove, and then you see it will take long for water to start boiling. Okay, it's not that easy. So it will take a lot of heat, and then for the temperature to change to 100, it will take a lot of heat. So you're losing actually a lot of units in terms of the power supply. So this is what happens even in a liquid refrigerant. So for it to change to gas, meaning it has absorbed a lot of heat, and then that's when it will change to gas. So a lot of heat will be absorbed before it changes to gas. The second advantage is the isothermal nature of this refrigerant. Okay, the isothermal nature of vaporization, it being that as it is evaporizing, the process is happening at the same temperature, meaning there's no compromise on the temperature gradient. The transfer of heat is constant. The gradient is still big, and it will be maintained. These are the two major advantages which this system has. Okay, so let us look at some of its components and how it's being arranged. Okay, so this is how every system which employs vapor compression system has, okay, in common. These are the major components. You have got an evaporator there. Okay, so this is an evaporator which provides the extraction of heat, and we have got the compressor. This is a many component of the simple vapor compression system. And then we have got a condenser and the evaporation, this expansion device. So I'll start by process 1 to 2. This process 1 to 2, it represents the absorption of the heat in a space. It could be in the office, it could be in the fridge inside, it could be anywhere where the heat has to be absorbed. So evaporator extract it. So inside those pipes, the conduits, those pipes, there is a liquid refrigerant which is flowing, and then because the environment outside is very hot and the environment inside, the temperature of that refrigerant is very low, -40. So it will start absorbing that heat from that environment, and then in the process leaving that environment cold. So as it absorbs that heat, the liquid will start vaporizing, meaning you start changing phase from liquid, which is in this pink, to this red or scarlet color. So this is just a change that this is now no longer the liquid, but it's what is in gas. We want mostly of the time that whatever we are supplying to the compressor must be gas, because if you supply the liquid refrigerant into the compressor will be overworked, meaning it has to do a lot of work to convert that gas, that liquid into gas, and to provide that more work of heating up the gas to a higher temperature. So we have to make sure that as we supply the compressor has to be gas. But there are certain situations which we are going to look at in the next topic, in the same topic, but in the next lecture, on where we supply a liquid refrigerant, which is wet, okay, mixture of gas and vapor. So this gas which is supplied to a compressor is then compressed. When you compress, you increase temperature and pressure. Okay, you compress it to higher temperature and higher pressure, such that this now refrigerant can expand, can release this heat now to the environment, because it's very hot, it's hotter than the environment, so it can release this heat to the environment. That's where now we employ the condenser. If you look at the back of the fridge, some condensers are hidden. Some, they employ some fan and the condenser. Okay, so meaning there's a fan and a condenser. So when the fan is blowing across the condenser, it's able to release that heat to the atmosphere. If you look at the radiator, okay, if you look at the radiator, it's the same principle on which these condensers work. So there is a fan, there is also the cores in which the refrigerant is passing. So the air is taking away that heat. Fridges, they've got cores at the back, and those cores, they expand the heat to the environment. So never, especially ladies, never should you confine the fridge in a corner. You push it against the wall. You are confining the air. So there must be some aeration. There must be some natural air, space for air to pass, to take that heat and the fresh air to come back and the dust and the like. So never should you decorate even the condenser. You know, if you go to some homes, they have put tablecloths on the fridge and the condenser and whatever. No, no. That place behind there has to be covered, has to be not to be covered, has to be left like that, because it's a place where the fridge is releasing that heat from what the heat system. So never allow children, those who are prayerful, when they go to pray, they come back late in the night and realize that they have to go to school, they go and their clothing by the fridge. Don't allow them, because you'll damage the system. Because that's where the temperature has to be released. And then, so this condenser releases that heat from the system. So this is high temperature. We release it. But this process of releasing again is happening at constant temperature, meaning you are releasing the heat, but the temperature is not changing. That's a pretty part of this system. So meaning the temperature gradient between the environment or the atmosphere and the condenser is still the same. So it will release more heat without it being compromised. Huh? So meaning this gas will change now into, now a liquid, very hot liquid, because the temperature is still high. And then this liquid, it will go into an expansion device. Okay. In a previous topic for gases, we are employing the turbine, okay, cooling turbines. And you can know that a turbine is quite an enormous device. It's not like a small device. But look at how minute this system is. Instead of putting a turbine, what they put is just a core for the fridges. Meaning you can shrink, you can confine this system in a small space. Huh? So instead of putting a big device like a turbine, you just put a capillary, okay? A capillary suffices to provide the work of reducing the pressure as well as reducing the temperature. So that's how this system is employed. So these expansion devices, as you move from system to system, is different. Okay. Others will look at each component in the next topic. We'll look at how these components are made and how they are employed. Kindly unmute or mute yourself. The one who has just joined. Kindly mute yourself. Okay. So let us look at the pH diagram. Okay. In this case, we'll be looking much on pH diagram. How this pH diagram influences the results. So let us look at the pH diagram. Look at this pH diagram. Just a minute. I get this book so that I show you the pH diagram for this. Okay, thank you. So this is the pH diagram, the pressure enthalpy diagram, okay, which we are going to be using. It has got boundaries, okay, within which we shall be drawing our cycle, okay. So the first one is saturated liquid line. You have seen this before in thermodynamics. This is saturated vapor line, and this region which is called subcooled. It's also a region where it's just liquid, it's not gas, mixture, but just purely liquid. And this region outside saturated vapor line is just superheated gas. This is where a vapor now behaves like a perfect gas, meaning it observes. Take note of this. In this region, the vapor observes the laws of perfect gases. So all the laws of perfect gases here in the superheated region are observed. So this is the pH diagram that we shall look at. Okay. So let's move on. So this is just the smart diagram of what the fridge is like. So I've got the evaporator, okay, somewhere there, which is picking up the heat, and then the gas leaves, it comes into the compressor adds more heat, and goes into this condenser. So you can see the things. So the condenser releases the heat, and then the liquid now goes back to this expansion device. Yes, so this is just a snap diagram of simple vapor compression system. Okay, so let us look at one type. Of course, there are a lot of types that we are going to look at, but today we'll look at this simple vapor compression system with the gas leaving compressor superheated, or vapor entering the compressor as a saturated gas. So let me just show you the systems that we are going to look at, and obviously next week or after next week we may do some tutorials. If things goes well, we may do some tutorials. So let us look at okay. So let us look at some systems or the cycles which we'll look at. Okay, and when the next topic, when I start these cycles, it will be brief. Okay, we'll concentrate much on the calculations, because most of the things I would have explained. Okay, I will explain it today. Okay, so cycles with dry saturated vapor after compression. Okay, so meaning there is a cycle where after you compress, it ends up on the saturated line. And then a cycle with wet vapor after compression, meaning after you compress, it's still wet vapor, meaning there is no gas coming out, still it's a mixture. So a cycle with superheated vapor after compression, cycle with superheated vapor before compression, a cycle with undercooling or subcooling of the refrigerants. So we'll look at this next time and next week, so that quickly we may understand these cycles. So this is what we are going to be employing in all the calculation, these cycles. Hence, we need to know all of them. There are about 5. So when choosing what question to bring, I may choose among these. That's how good this course is. So I may choose among these. So you just need to learn to understand these cycles. Okay. Let's look at. Let's continue with this. So today we'll look at this cycle where the entry to the compressor is vapor, concentrated vapor, and whatever is leaving the compressor is superheated vapor. Okay. So from point 1 to point 2, we may assume starting from 4 to 1, this process, because that's where our concentration is. Want to know how much heat have you absorbed? So if you move, say, from this liquid line to the saturated line here, okay, from here to there, you can see that as you draw the line, as you move along that line, you are absorbing the heat, but there is no change in what? Pressure and temperature. You can see TL meaning lower temperature, and TH meaning higher temperature. There is no change in the temperature, meaning you are absorbing the heat at a constant temperature. So the heat that you are absorbing is called the latent heat, the hidden heat, meaning it's not changing with as you change with temperature. But as you move away from these saturated lines, then the heat becomes sensible, meaning it will be changing with what? Temperature. Okay, so what you're observing, so the bigger the gap between 4 and 1, the more heat you have absorbed. So our goal and our interest most is to increase the gap between 1 and 4 so that we can absorb as much heat as possible. Okay, so for 1, this process represents the extraction of heat, okay, the removal of heat absorption. And then from 1 to 2, this is 1 is the entry point into the compressor, 2 is the exit point of the compressor. So the vapor enters into the compressor. You can see that this is a saturated vapor line. So vapor enters into a compressor. The compressor does its work by compressing, increasing the temperature as well as the pressure. So whatever is exiting the compressor is of higher temperature and higher pressure. So now is has to be rejected, has to be expended to the environment. So the condenser now is brought in. So you employ the condenser now to start cooling this. Okay. So when it's rated, you can see this is same pressure, but the temperature is different. Okay. So as you are cooling, you reach a point where this point now, which we call a dew point, meaning start, it is initially gas. Okay, it's initially completely vapor, but you are cooling it. You are cooling it, and then eventually there will be some drops here. That's why we call it this point a dew point, and then you will start cooling. This now becomes now mixture of liquid and vapor until it eventually reaches what? Liquid. So before it goes into the expansion device, it has to be liquid, no mixture of vapor and liquid. So in the expansion device, it is expanded, but the process is at constant entropy, and you know, it's like a orifice. You punch a hole, and then you allow this water from big, you know, like a container, if filled with water, and then you just punch a small, water will start coming out. So the throttling process, that is what we call throttling process. It will reduce the pressure as well as the temperature. Besides that, you can employ the principle of pipes. You know, if you have got a longer hose pipe, you connect to a tap. Because of the length of that hose pipe, the pressure at the end of the pipe will be very low because of that length. And then also the diameter of the pipe matters. If it is very small in diameter, it will also reduce the pressure and temperature. But if you cut that pipe into smaller pieces and connect to the tap, you see that the temperature, I mean the pressure will be very high, as well as what the discharge will be also quite high, because the resistance that is coming as a result of length is very small. So that's why you see when you look at the fridge at the back there is that what we call a capillary tube. That capillary tube is cold, meaning it may look small into your eyes, but when you stretch it, it's very long. Because of that lengthy and then very thin diameter, the liquid is constricted in that, and then because of the resistance, then it loses the temperature and the pressure. That's what happens, and then you will come back. So the liquid come back cooled, and then it's able to pick up more heat from the fridge or any space, and the cycle repeats itself. So this is how this cycle works. Okay. So this is a pH diagram. So take note. Take note. There's TS and pH diagram. In pH, the process 3 to 4, which is expansion device, the process is constant. Okay, because it's constant because the entropy does not change. Okay, so take note of the diagram. So let us look at the processes, the compression process. This one, 1 to 2. This is compression process. As you are compressing, initially this refrigerant at point 1, it has got an enthalpy, the amount of energy it's possessing. So as you compress, you are adding some more heat to it. You're adding more energy. So at point 2, it will have new enthalpy, to have new amount of energy. So to know how much work you have done is by finding the difference, H2 minus H1. It will give you how much work you have done per unit mass, okay? If you see small mass, HH, that implies that it is per unit mass. So that gives you how much work you have done to achieve that refrigeration effect. So condensing, you want to know how much have you released to the environment, okay? So you can also find how much you have released by comparing the H2 against the H3, okay? So you compare H2 minus H3. You can know how much you have released to the environment, okay? So the expansion device, okay, on this one, there's no work, there's no change in enthalpy, so there's no work, okay? So they just decrease in temperature and pressure. Vaporizing process, this is our area of interest, okay? Want to know how much heat have we removed from the space. So you compare the enthalpy at point 1 against the enthalpy at point 4. But take note of this diagram. Point 4 and point 3, this one, because of enthalpy, constant enthalpy in expansion or in a throttling process, point 4 and point 3, the enthalpy is the same. So H3 is equal to H4. And then, on a liquid line, from steam tables, we know that the liquid has got the enthalpy, which we call HF. Okay, so from steam tables, you can find that HF depending on the temperature. Yes, so most of the time, we'll be seeing that HF, don't be surprised. It will imply the enthalpy of the refrigerant on the liquid line. So want to know how much have we extracted there. So H1 minus HF3. Okay, HF meaning the enthalpy of liquid at point 3. Okay, so that will give you how much energy is in liquid against that vapor pressure. So when you find the difference, then you will know the refrigeration effect, how much heat you have extracted. Now to find the efficiency, okay, or the coefficients of performance, you need to compare what you have removed against the work done to achieve what is removal of it. So which is the refrigeration effect against the work done. That will give you the COP. So the major work that we'll be doing, especially in your calculation, is to find this enthalpy 1, enthalpy 2 at every point. First thing is find enthalpies at every point, and then you are good to go to answer any question. Okay, this just give you some of types of refrigerant that are used in vapor compression systems. There are quite a number. Okay, the old ones which were being employed there were called chlorinated fluorocarbons, fluorocarbons, CFCs, CFCs. So, but now they're no longer there. They are being phased out because of their impact on the ozone layer depletion. So these are being phased out, but they were being used. So look at the boiling point. So the boiling point at the point at which vapor start forming. So you can see this is R23, R11, it has got a boiling point of minus 23, meaning it can absorb any temperature, even at 0 degrees. If you put anything in a fridge at 0 degrees, it will lose it to this refrigerant because its boiling point is at minus. The other one is minus 29. You can see this is R22, it's minus 40. So these have got lower boiling point, so meaning they can absorb a lot of it. Yes. Okay. So let me just look at some of the factors that affect the factors that affect the performance of vapor compression. So these are key, and then we can call it a day and then look at other things next time. So one of those factors are subcooling, okay? Subcooling of liquid, meaning in the normal system, there's no subcooling. Subcooling is where you cool that condensed liquid beyond that liquid line. That's what it implies by subcooling. So look at this. This is a normal pH diagram. It is A, B, C, D. That's the normal, okay? But when we subcool, meaning we reduce further the temperature of the liquid, okay, which is coming from the condenser. We reduce it further by passing it through the heat exchange and what. So it will no longer leave the condenser at point D, but it will leave it at point D prime, meaning it will leave it at lower temperature, not at 35, but at lower temperature. In a TS diagram, let me try it and see whether I can manage to draw this. So in a TS diagram, instead of leaving there, it will follow this path and leave somewhere there. Okay, so it will leave at a lower temperature. It will leave at a lower temperature. So initially it is at this point, and then because of subcooling, you see it going down and it leaves there, meaning at a lower, because this is temperature diagram. So initial temperature is there, and then this is at a point where it will leave expansion, the condenser. So meaning you have subcooled it, you have reduced it further. That's what subcooling means. So let's look at the impact. What's the impact on the COP? Yeah? What's the impact on the COP? So because that's our goal. Are we increasing the COP or are we reducing the COP? Okay. So look at this. I said this line represents the amount of heat you have extracted. Okay. AB represents the amount of heat you have extracted. But as you have subcooled here, A goes to A prime. So the new amount of heat that this system will absorb, it will be from A prime to AB. So can you observe and see that the difference between A prime and AB is bigger than the difference between what? The A and AB. So this one, AB, enthalpy at B minus enthalpy at A prime is greater than the enthalpy at AB minus enthalpy at A. So this results in an increase in what? The COP. So there is an improvement or improve the COP by subcooling. So this is the impact of the subcooling. When you subcool, you increase the COP. Okay. So what is the impact of superheating? Okay, you superheat before this refrigerant leaves the evaporator, you superheat it. So meaning that it doesn't enter the compressor as saturated vapor, but it will enter as superheated vapor. Okay, this is this one. So this is the one. Okay, so we have got the initial diagram A, B, C, D, and then so as you want to superheat this refrigerant, meaning you provide more heat. Okay, this happens even when you know some people have got a tendency not understanding how a fridge works. Just pick up the food or anything from the stove or from the brazier and take it straight in the fridge. So because of that high intense heat, the refrigerant will be superheated, meaning you leave the evaporator superheated. So that will make the compressor to overwork. Because if you compare the difference between this point and BH and BC, there is an increase in amount of work that has to be done, okay? Which in the process may increase the COP because there is an increase also in the amount of it absorbed. But in most of the time, there is no increase, huh? There's no increase. So COP may increase, decrease, or remain unchanged depending upon what the range of pressure of the cycle. So this may increase or not increase. Yes. So that's what happens. So what happens when you change the pressure in the suction pressure? So you want to change the suction pressure of this compressor. Okay. So initially we have got A, B, C, D as usual, or A, B, C, D, A, B, A, or C, whatever. So now we reduce that suction pressure. Initially it is AB, but we reduce it to what? A prime and B prime. Okay, what is entering into the compressor now, a pressure is reduced to 1 bar. It was initially 2.6 bars, but we reduce it to 1 bar. What happens? Let us observe this. You know, this pH diagram, it has got this envelope-like thing that covers or the shape or the profile within which this diagram or the calculation has to be done, these lines. So you can see that it is increasing or reducing on top, also reducing at the bottom, just bulging in the middle. So since it's reducing at the bottom and also on top, so when you reduce the pressure, meaning the space at the bottom also reduces. So this is what happens. So when you reduce the pressure, you go there and you can see there is also a decrease. Okay, there is a decrease in the amount that, I mean, energy that you have to take. Okay, so there is a decrease because this point now has reduced. You can see where B is and B prime where it is. So even if you are to maintain A, but B has reduced, has gone in. So AB, the amount of energy extracted is greater than the amount of energy that you get from A prime and B prime. So what happens when we increase the discharge pressure? Okay, same applies. So when increase the discharge pressure, meaning we just increase the amount of work that the compressor has to do. And since this profile or this cycle is changing, okay, on top, then there's that reduction. Okay? Initially, it is at D, and when you increase this discharge pressure, it goes at D prime. So you can see that there is that reduction in the amount of energy or heat that we are going to extract. So that reduction, it leads to reduced COP. So increase and decrease of pressure reduces the COP. Okay. So this is the few impacts that happens now on the COPs. So next time when we schedule a meeting, I presume that time we'll resume the contact classes. We just need to do more of the calculations. We need to do some tutorials. And after this, I'm sending the assignment, okay, due next week, Wednesday. So this assignment is due next week, Wednesday. So you need to submit it. It's online. It's not like where you have to go and negotiate with me that I was sick. No, it will tell you that this is the time when this assignment has to be handed in. If you don't submit on that time, it closes in. You can't fight your system. And when I move in to go and check, I want to repeat those who submitted and I'll mark only those who submitted. So there's no compromise on the time of submission. It's online. I'll give you the link. Okay. Either I'll give you it on Moodle or on Edmodo, either platform I can use it. So I'll communicate on which platform to submit this assignment. Okay, it has been a pleasure having you on this. If there is any question, you can ask now. Now it's open.
Sir, are you going to send us the notes?
Yes, yes, I'm going to send you now through a classroom.
Okay, thank you.
All right. Some more questions? If there are no questions, then we call it a day. Yeah. Call it a day.